Hi everybody. Welcome to the lesson on analysis of variance, which is called ANOVA. So it's abbreviated ANOVA. This is the test to compare more than two means. So when we did the independent samples t-test, that one was comparing just two means. If we want to include a third or more in the comparison, then we need to do an ANOVA. This ANOVA that we're doing today is the most basic version of ANOVA. It's called the one-way ANOVA, but it's not the only version, and it's not the last version of ANOVA that we're going to see this semester. We're going to see several variations on this. So I think it's important to make sure you kind of understand the concept before we go on. So an example of this, using the same attention span data set, and this is probably going to be the last day we use that data set for a while, if you're getting tired of it. We want to compare the mean amount of time children spend watching TV based on their family structure. So looking at this data set, we've got one of our variables that we've seen before is the amount of hours per week spent watching TV. And then the one we haven't seen yet is the household structure, which is single parent, both parents, or a parent and a step parent. So those are our three options. And I should say this is not to be exclusive of other household structures. I'm sensitive to that as well. That's just only the options that are in this data set. Okay, so when you have an ANOVA, again, we said we want to compare across groups. So we want to compare the mean of the first group to the mean of the second group to the mean of the third group. When we're doing it this way, just like we had before, the numeric variable is the dependent variable, and the grouping variable is the independent variable. So we're kind of wanting to use the group to predict, in this case, the amount of time a child spends watching TV per week. So this may seem a little bit, I don't know the right word, esoteric for now, but later on, this gets to be more helpful, I think, in understanding what these analyses are doing. So, in the ANOVA, your null hypothesis is always that all of the means equal each other. Here I put mu1 equals mu2 equals mu3 because we have three groups. But if you've got more than three groups, you're going to have, if you've got 5 of them, you're going to add equals mu4 equals mu5. Now, the alternative hypothesis, people are always tempted to want to say mu1 is not equal to mu2 is not equal to mu3. But that's not actually the opposite of all of those means being equal to each other. The only thing required to be opposite from all means being equal to each other is that there's at least one that's different. And that's the alternative hypothesis here. So I don't want you to make that mistake. All right? So the alternative hypothesis is that at least one of the means is different from the others. So we said we've done the independent samples t-test. And there are a couple differences here. One is that if you're doing more than two groups, again, you have to do an ANOVA. The independent samples t-test cannot accommodate 3 or more groups. Technically, you can use an ANOVA for 2 groups. So if you don't have more than 2 means, but you still want to compare 2 means, you can do an ANOVA. However, the independent samples t-test is better for that scenario because the ANOVA does not have the ability to do one-tailed. Okay, whereas the independent samples t-test does. So I put here test to compare more than 2 means. Technically, ANOVA will compare 2 or more means, but we usually don't use ANOVA to compare exactly 2 means. That's usually the independent samples t-test. So now I want to answer the question, why is this called analysis of variance when it's actually means that we're comparing? And answering that question gets at exactly what is analysis of variance. What is it doing? So to look at that, let's look at these 2 pictures here. Each of these red things that, to me, these look like medicine capsules. But each of these represents a group. So in this picture, we've got 4 groups that are being compared. Well, there's 2 kinds of variability that we might see. There's the variability within each group. So if you look at how wide each group is, and I'm going to start typing here. Oh. So we've got this within group variability. This is how much variation exists within each group. Okay, this is how wide each group is. Okay. And then there's this other kind of variability called between group variability. And that's how far apart the groups are from each other. So if you look here at this top picture, these group means are not all exactly the same. But I think it's a little bit hard to tell if there's really a difference between them because there's so much variability within each group. If we compare that to this bottom picture, and I'm going to go ahead and write this down. So in this top picture, we've got, I think, a large within group variability. And I think in comparison to that, these groups are not very far apart, which means we have a small between group variability. So that's in this top picture. In this bottom picture, on the other hand, each one of these groups is tightly clustered together. So within each group, we don't have too much variability. So here we've got a small within group variability, and within group is WG. But we have a large between group, which is BG. Not like the musical group from the 70s. This is between groups variability. Sorry, I guess my jokes may not go over as well on video. Anyway, but so up here, the groups aren't very far apart from each other. And it's even harder to distinguish because we've got so much variety within each group. On the other hand, down here, it's easy to see the differences between groups because the groups are far apart from each other, and within the groups, they're pretty close together. So, if we have a situation like this top one, this is going to be weak evidence of a difference across groups. Whereas down here, this is going to be strong evidence of a difference across groups. So the short answer to why is this called analysis of variance when we're actually comparing means is that we're parsing out the variability into two different kinds, and we're comparing them to each other. We're comparing to see where is the bulk of the variability. Is it between the groups, or is it within each group? Okay, so one piece of terminology you might see, just in case you see it somewhere, is that the between group variability is also called variance due to the factor, meaning this is due to the group membership, whereas within groups is sometimes called error. And the error just means that that there's not really, I'm accidentally writing on here, there's not really a difference, it's noise. Okay. So here we have, assuming that there is actually a difference between groups, we have this, what's called the signal, which is the fact that the group means are different. And then there's the noise, which is the fact that there's some natural amount of variability to be found within each group anyway. But there always will be, that's unavoidable. So the way we do this is we look at something called the ANOVA Table. And anytime you look at output on an ANOVA, it's going to be accompanied by an ANOVA table. There are some key things on here you need to know. So the SSB or SSBG, or sometimes called SS factor, is the sum of squares between the groups. Okay, so it's sum of squares as in, and I'm going to write this off to the side just because I don't want you to think that this is directly referring to that. If you remember back when we talked about the standard deviation, we looked at the sum of the x minus the x bar squares, and then we said that was the sum of squares, and then we took the sum of squares and divided it by n minus 1, and we said that was s squared. Essentially, that's what's going on in this ANOVA table. Basically, we have this raw amount of variability under our SS, that's the sum of squares. The This one down here, the equivalent thing is called the mean square. So this is on the top, sum of squares, whereas this is the mean square. This is less important to us, not the s squared, but the mean squared on the table. But I want you to know that this sum of squares tells a raw amount of variability that doesn't account for sample size. Okay, so the sum of squares is the raw amount of variation without accounting for sample size. This is going to matter to us in a little bit. All right, so let's go back over here and look at this table. So the SS we said was this raw amount of variation that's between the groups. This is the raw amount of variation that's within each group. If you add them together, you get a total amount of variation. Okay, so here we have absolutely literally parsed out the variation into the amount that's between the groups versus the amount that's within the groups. Okay, and then we do some division here by the degrees of freedom, and this is a variance estimate here, like what I mentioned a minute ago. Although over here, yes, I wrote that as s squared. I was a little worried that I wrote that as s. This F ratio is our test statistic. So on an ANOVA, the test statistic is an F. So this is just a different distribution that we use for ANOVA. There are tons and tons of different probability distributions, and this is just one of them. I'm going to go back up here and talk a little bit about this F ratio, though. If we look back at this picture, we said that a large within group variability and a small between group variability, that combination is not good evidence of a difference. What we hope to see is a large between group variability and a small within group variability. So this F ratio is actually the ratio of the estimate of the variance between groups to within groups. Okay, so the test statistic is an estimate let me say it this way. It's a ratio of the estimates, not an estimate of the ratios. It's the ratio of the estimates of between group variability to within group variability. Okay, and we said we wanted between group variability to be large and within group variability to be small. So large values of our F ratio are stronger evidence of a difference. So this is stronger evidence of HA. So when you have large values of F, you're going to have small p-values. We're still conducting the test by p-value. All this is I almost said long-winded. I think it's necessary. I won't apologize for explaining how this test goes because I do think it's important. And it's also very accessible. It might take a little bit of time to process it, but I think it makes a lot of sense. And to me, this is kind of what's cool about statistics, is seeing that, you know, these formulas don't come from nowhere. They actually do make sense if you pick them apart a little bit. So anyway, large F also gives you small p-values. All right, so let's go over to SPSS. And we've got our data set up already. To get to our ANOVA, the easiest way is to go to Analyze, Compare Means, One-Way ANOVA. Okay, remember, one way is the most basic one, the one we're starting with. So that's under Analyze, Compare Means, One-Way ANOVA. We're going to go ahead and do the main test, and then we'll talk about assumptions and effect size and all that. So that's coming, but I wanted to go ahead and do this first. So Analyze, Compare Means, One-Way ANOVA, and we're going to take our numeric variable, put it under dependent list. So that is the number of hours per week spent watching TV. And our factor is household structure. So that's going over there. So if you click OK, it doesn't give you a whole lot of output. But this is it. And I'm going to copy that over here so we can draw on it. And as soon as it shows up, there we go. So the two things you need to know here for now are, this is your F test statistic, and this is your p-value. Okay, so F is your test statistic, and where it says sig, that's your p-value. And all this stuff we talked about on the ANOVA table, the sum of squares, the degrees of freedom, the mean square, those are all here. And I could give you the formulas to do all of this. It would be totally doable. I did them when I was in college, but I just don't want to spend your time doing that right now. If you want to look up those formulas, that might help you get a better handle on what's going on here, but I kind of doubt anybody's going to take me up on that offer. All right, so there's our test statistic, there's our p-value. This is our sum of squares between groups, sum of squares within groups, and our total sum of squares. Point that out because we're going to come back to that when we get to effect size. So when we look at our results, our null hypothesis, because we've got three groups, is mu1 equals mu2 equals mu3. Our alternative hypothesis is that at least one of the means differs from the others. From this SPSS output, we got our F as 32.899 for a test statistic, our p-value is showing up as 0.000, but if you remember, we don't actually write p-values as 0.000. We just put p less than 0.001. It's a little bit more of a professional way to write that. So this tells us that at the 0.001 level, we would reject H0 and say that there is sufficient evidence to conclude that at least one of these means differs from the others. Keep in mind, this at this point does not tell us which means differ from the others. It doesn't tell us if one of them is bigger than the others. It doesn't tell us anything other than these groups are not all the same. All right, so I think that's a good point at which to stop this video, and we'll pick up with the next one momentarily.